This is the ninth lecture of the year so far, and we're going to just slowly discuss the spin angular momentum in a general any direction n. So, summary of what we've recently talked about: we introduced operators, which were mathematical objects that act on kets and result in another ket, and we discussed how observables are represented by operators. And that if you take a measurement of some given observable, the result of that measurement is one of the eigenvalues of that observable, and the state of the system after that measurement is the eigenvector that corresponds to that measured eigenvalue. So we've done that. Today, we're going to look at, we've discussed the spin angular momentum. We've looked at it primarily in the z direction, but we've also discussed the x and the y components or projections of that spin angular momentum. Today, we're just going to go through the case of the spin in an arbitrary direction n. So first, let's consider what we mean by a general direction n. So we have our Cartesian coordinate system here, and we want to know that this n unit vector is pointing in the direction we're concerned with. And we can write that n vector in terms of its x, y, and z components. And you can just sort of see here that if I draw this right-angled triangle, the z component is just going to be the magnitude of that n vector, cosine that theta angle. Likewise, this side here, or this line down here, is n hat sine theta. Sorry about that sloppy writing there. So now we can, knowing that that's the length of this side of that right angle triangle, we can then look at the x component. You know, we have this right angle triangle here where the hypotenuse is n hat sine theta. So this x component here of that n hat vector is going to be the magnitude of the n hat vector, sine of theta, which is the hypotenuse of this right-angled triangle that I've drawn here, and it's just cosine phi of that. If we just use our trig, cosine is adjacent over hypotenuse, so bring the hypotenuse up, which is that, and that's our x component, and we can do the same thing for the y component there, which is just going to be n hat sine theta, which is the hypotenuse of that triangle, of this right angle triangle there. And we're now looking at the opposite side of that azimuthal angle, so that's going to be sine of phi. So we can look at the geometry of a general direction and break it into components, and we have the x, y, and z components of that general direction. Keep in mind the n hat vectors, it's a unit vector, so those are all just one. I've written them there just to be explicit. What about the spin operator? Well, we're essentially wanting to project the spin angular momentum onto that direction. So we're just going to take the dot product of some spin vector onto that n hat direction. And what we're going to do is we're going to think of that spin vector as basically being the x, y, and z components, or the projections of the spin in those directions in the x hat, y hat, and z directions. So when we take that dot product, we're essentially getting the x spin x operator dotted with the nx plus the spin y with the y component of that general direction vector, and likewise with the c unit vector. So we end up like this, and we're going to want an operator in this, and we're going to look into our matrix representations. So we need to recall what our x, y, and z spin operators were. And they're right there from previous lectures in your text. We've already been through these, and we know those are our operators, so we can actually write this S sub n, or the spin in the general direction operator, in matrix form now. And we get these three terms, and we can just add those all together. And we end up with this, where I factored out the sine theta from the off-diagonal terms, thanks to the fact that cosine's even, cosine phi is equal to cosine negative phi, and that sine is odd, negative sine phi is equal to sine of negative phi. We can actually use Euler's equation and take the bracketed terms on the off-diagonal elements of that matrix and convert them into exponentials. And we end up finally, after all of that math or algebra, the matrix representation of our spin operator in a general direction. So that's how we get here. For homework, one of the homework things I'm going to give you is you're going to have to diagonalize this matrix or this operator. And when you do so on the homework, you're going to get sort of results. Well, the first result you're going to get is that the eigenvalues of this operator are h bar over 2 plus or minus h bar over 2, kind of like we'd expect. We know spin it's a spin 1/2 system. It's quantized into h bar over 2 plus or minus. There's nothing special about the z or the x or the y or any real direction there. And the eigenkets or the eigenvectors are spin up in the n direction and spin down in the n direction, and are given by these formula here. The reason why this is sort of important, and I like this representation, is that either of these, the spin up or the spin down, we'll focus on the spin up in the n direction, can be used to describe an arbitrary ket in our spin 1/2 system. So any general ket can be described this way. And to see that, we're going to just write down a general ket. So what we've been doing so far is using the z bases. So we have spin up and spin down in the z bases, which are complete. And we know that any general vector can be described as a linear combination of those because they form a complete basis. With a and b both being complex numbers. Now, that means that a and b can both be written in this exponential form where they have some magnitude and some complex phase I've called theta sub a or theta sub b. So just rewriting that, we have the general vector can be written in terms of those, and we can factor out the phase of the spin-up state. And what that does is, well, the global phase that we've just factored out in quantum mechanics in these generalized kets is arbitrary. It has no physical meaning, so we can change the global phase to essentially whatever we want. So we can factor that out and then just get rid of it, and we're left with just this relative phase phi, and we can write that generalized ket, that psi, as using this: a spin up plus b e to the I phi spin down. Now, we haven't really done much here. We've just done some mathematical, rearranging here. But what we can do is we can then take the normalization condition, which is these vectors are normal, so a squared plus b squared is going to be equal to 1. The magnitude, the inner product of that vector with itself gives us 1. And we can rearrange that to define that magnitude b in terms of a, and we can finally rewrite that general ket this way. And from there, if we just kind of parameterize a, the magnitude of a, as cosine theta over 2, we see that substitution and a trig identity there gets us that's the exact same as writing our spin up in the end state that we had in the previous slide there. So we can write spin up in a general direction in that form, but we could also write any general ket in that direction. We just give it some theta and some phi, and we've got that. One of the reasons that I think this is important to bring up is it's actually a nice way of mapping two-state systems, and this is used in quantum information a lot. Hopefully we'll get into this a little more later in the course, but you can define any, not just spin 1/2 state system, but any two-state system, call one state 0, one state 1, and you can sort of represent that on what's called a block sphere. So you describe any arbitrary two-state system with the two states, the basis states 0 and 1 on the top and the bottom. It's a two-dimensional Hilbert space. So you essentially need what that means is you need two numbers to describe any general vector in that space. In the state way we've been writing it, it's just going to be a linear combination of that 0 and 1 state, whatever they are. A and B would fully define that state. What we've just sort of shown is we can also use theta or phi to fully describe that state. And what that means is you can represent any pure state in that Hilbert space as a point on that sphere described by those two angles. And what happens, why that's useful, is you can perform operations and look at the evolution of that system as basically rotations and motion around that block sphere. So we're not going to get into any more detail on the block sphere now. Hopefully later in the course, when we get to time evolution and that, we'll be able to come back to it and start to see how it's useful. But yeah, the general state for spin in some general direction and actually maps to this block sphere quite well. So that's it for this lecture. Next lecture, we're going to start talking a bit more about operators. We're going to discuss what Hermitian operators are and projection operators and go from there and start discussing measurements, which will finally bring us into the formal analysis of those, the final Stern-Gerlach measurements we used to introduce all the quantum weirdness and that in the first chapter of the course.